we have set up the basic framework of ellipsoid method and the tools by which we handle the sizes of partials of the spaces, which is ellipsoid, to implement the ellipsoid method algorithm. Let's see what the method is. So what you do, you have this kind of input. When you say x less than equal to b, I want to find a satisfying assignment, and we create a ball of this size. It's centered on the origin, and it's a very large radius, such that the whole of the polytope ax less than equal to b bound to be inside here. Because remember that all vertices should be smaller than this point, and so the whole polytope, and we have assumed that polytope is bounded, so therefore all these whole of the polytope will inside this ball. Okay, so we started with a very large ball which contains this ax less than equal to b. Now what do we do is see if the center of my ball satisfies ax less than equal to b. If that is the case, we are done. We have satisfying assignment. If that is not the case, then there will be some linear inequality ax less than equal to delta, which is violated by my center. Okay, so let's suppose ax less than equal to delta is that inequality. So we say that now I'm going to cut this my ball and cut into find a smaller ball that contains ax less than equal to b. How do we do that? We cut in we basically find the covering of ellipse which cuts the ball in the following way, that it cuts in the a direction and from the center z, and find a new ball. Okay, and in this new ellipse we update the value of z and the matrix A. And if my ball becomes too small some point of time, because of this lower bound on the size of the volume of ax less than equal to b, we know that my input constraint is unsatisfiable. Then you return unsatisfiable, otherwise you go back. So let's look at an example which will make it very clear how this algorithm proceeds. So let's suppose this is my polytope in a two-dimensional space, and we start with a ball which contains this node. Okay, this triangle. Now what we do, we check that if my center of this ball is inside this ball. If it is not the case, we check if which linear inequality is being violated. Look at this. We have this polytope defined by 3 linear inequalities, and you can check that these two satisfy this point, but this third one does not. Okay, so what do, you basically, in this direction, which is this parallel to this direction, we're going to cut this ellipsoid. Okay, and once you cut this ellipsoid, we get this smaller space like this, which we want to represent again using some ellipsoid. And remember that we had this procedure, and then we get this red ellipsoid which contains this this triangle space. Okay, now we again check this my center of my inside this satisfies this polyhedral. If it does, then we are done. If not, then we go and find the smaller and smaller ellipses. So this method is going to run in a polynomial time, and here is the bound is written. Why that is the case, you can actually have guessed it by now. That initial is exponential size in terms of the n and the numbers appearing in your matrices. The volume threshold is again this number, which is exponentially smaller, and with respect to same numbers, and each time we make a step, my ball becomes some constant time smaller. And then you can just do the calculation that in these many polynomial steps you will hit this small size. Therefore you will you're going to solve your constraints, therefore you find a satisfying assignment in a polynomial time or not. So this method in theory is polynomial, but in practice it's inefficient, because the algorithm depends on the size of numbers, and the number of steps are actually dependent on the size of size of the input numbers. And again and again, if you look at this computation of the new the smaller ellipse, you can see that it at some point of time it computes square roots. That means you need a high precision computation, and then you need to approximate these numbers, and you need to also show that those approximates do not violate your desire to keep containing this triangle. Experiments also show that it cannot compute with simplex, so even though the method is polynomial, it's practically useless. However, later on, Karmakar improved this method and come up with a new method, which is which is named after his name, and this significantly improved the performance.